For hypothesis testing from independent samples, we analyze the two sets of data sort of individually and then pull the information together. So the first step would be to find the mean, y bar, and the standard deviation, s, for each of the two samples. Then you use these to sort of calculate the observed value of your test statistic, the t-score, which in the numerator we will have the difference in the two sample means, y bar from the first sample minus y bar from the second sample, minus the difference in the population means, mu1 minus mu2, then divided by the square root of the standard deviation squared over the sample size for the first sample plus the standard deviation squared over the sample size for the second sample. Now in this course we actually only look at a null hypothesis where the two populations are equal, which means the means are the same. So if you have the same number and subtract it from itself, you're going to get 0. So really that numerator can just become the difference in the two y bars because you're sort of subtracting 0, which doesn't change anything. Now this thing has a t-distribution where the degrees of freedom are a little bit complicated to calculate, and we're just going to let the computer give us the degrees of freedom to use, or it'll be given in a problem. There's a formula that most of you probably do not want to see that does that. Now for a hypothesis test to be valid, you need to take two samples, right? It's independent samples. So you take two samples, one from each of your populations, and they have to be random, right? So you take a random sample from the first population and a random sample from the second population, and they're collected independently of each other. Secondly, the populations are either going to be normal themselves to start with, or you need to have sufficiently large sample sizes. So you want N1 and N2, your two sample sizes, to be 30 or more as our rule of thumb for the course. And lastly, the population standard deviations are unknown. So sigma 1 and sigma 2 are unknown. So you're going to use the sample standard deviations, S1 and S2. If you think about it, these are pretty much the same things you do in the one population mean inference validity checks. You just have to do it twice. Let's look at an example. Is the mean selling price for houses south of Center Street in Provo different than the mean selling price for houses north of Center Street in Provo? So imagine the city of Provo, and you have a street in the middle that runs sort of east-west, and you have houses north of it and houses south of it. And we want to know, on average, or in terms of the mean, is there a difference in selling prices of houses based on location? A random sample of selling prices of houses in both locations were selected, and you may assume the selling prices are normally distributed. Okay, so when we do the validity check and think about it, we're going to know at this point, okay, the population's selling prices were already normal, so I can actually take smaller sample sizes. The mean price for 18 homes north of Center Street was $127,000 with a sample standard deviation of S equal to $2,400. The mean price for the 18 houses south of Center Street was $125,000 with a sample standard deviation of $4,800. So that's all your background. Now, is there evidence of a difference in mean selling prices using a 0.05 level of significance? And for this example, use 25 degrees of freedom when trying to locate the probability. And I'm going to walk through this one sort of by hand and show you where all the math comes from, and then we'll come back and do it in the software and talk about what the software output looks like and how we would interpret it. So first we need to make sure we understand what our parameters are and what we're testing. So mu sub n minus mu sub s is the mean cost of all houses north of Center Street minus the mean cost of all houses south of Center Street in Provo. Okay, so it's that difference. Now start with the alternative hypothesis. H sub A is that mu sub n minus mu sub s is not equal to 0. So what that means is they're not the same, right? And that's what we're looking for. So this is a two-tailed test. Is there a difference? We're not specifying are houses north of Center Street more expensive. We're just saying, are they different? So this is a two-tailed test. Under the null, we'd say, no, they're the same, right? So mu sub n minus mu sub s, if they're the same and you subtract them, you would get 0. So that's why we have h sub 0 being that mu n minus mu s equals 0. Now our decision rule is going to be to reject the null hypothesis, h sub 0, if the probability p-value is less than or equal to our level of significance, our alpha value, which was 0.05. Next comes really where the arithmetic comes in on this problem. So we would write down the form of the test statistics. So t equals, okay, in the numerator we have the difference in the y bar. So we'll have the y bar for north minus y bar for south. Remember, we would subtract what the null hypothesis says the difference in the mu values is, which is 0. In the denominator, we have the estimate of how different the difference in y bars would be. Okay, so it's the Sn squared over n sub n, that's the north standard deviation squared, okay, over the sample size, plus S sub s squared over n sub s, so that's the south region stuff, right? So that is the standard deviation of the prices in the south squared over the sample size of 18. And this is going to have a t-distribution which we were told to assume has 25 degrees of freedom. Okay, so the calculation would be 127,000 minus 125,000 for the numerator, so that gives you a difference of 2,000. In the denominator, the square root of all that stuff turns out to be 1,264.91106. Okay, so when you do that calculation of that fraction, 2,000 divided by 1,264.91106, and then you round that off to a couple of digits, you get the t-score is positive 1.58. Okay, so what would we do next? Okay, so we can double check and make sure it's valid and then move into calculating the p-value. Well, it is valid. The samples were independently collected and they were random. The population standard deviations were unknown, so we're using the sample standard deviations. And also we were told the populations were normally distributed in the statement of the problem. So the small sample sizes are not an issue because we were told we could assume the distributions were already normal. So it's valid to keep going. Okay, so the p-value is going to be the two-tailed probability, okay, or double the one-tailed probability. So remember, our test statistic was 1.58, so I want the area to the right of positive 1.58 and to the left of negative 1.58 for a t-distribution with 25 degrees of freedom. Okay, so what I'm going to do is go back to table T and show you where that comes from, but we're going to be getting that it's double something between 0.05 and 0.10. So if we go back to table T, remember we're at 25 degrees of freedom and we want to bound 1.58, right? So it's between these first two columns. So you can either read the two-tail probability and say my p-value is between 0.10 and 0.20, or it's double something between 0.05 and 0.10. Okay, so if you're doing the one tail, you have to double it, because remember we want the image that's the two tail. Okay, So that tells me that the red part, if I were at 1.58, which is between these two columns, the total area in red is somewhere between 0.10 and 0.20. So if my p-value is between 0.10 and 0.20, that tells me it's not small, it's not less than that 0.05 level of significance. So I'm going to fail to reject the null hypothesis as my decision, and then write my summary. At a 0.05 level of significance, there's not enough evidence. There's insufficient evidence to claim that the mean selling price for all houses north of Center Street in Provo is any different than the mean selling price for all houses south of Center Street in Provo. Now let's look at what you would do if you had StatCrunch output, because you're not going to do the calculation now, but all the other information is going to be there, and you're actually going to get a more accurate p-value. In this case, what you have is it tells you the hypothesis test results. We're looking at mu1 being the mean for the north category, so these would be the houses north of Center Street. Mu sub 2 was mean of south, so those would be the houses south of Center Street. And it's telling you under the null, you're looking at mu1 minus mu2 equals 0. So you're saying that the mean of north and mean of south are equal in that case. Under the alternative, it's saying they're not equal. So you can see it's a two-tailed test. You want to make sure you see the without pooled variances part there. If you have different sample sizes and if you click or unclick a certain box where it says to use or don't use pooled variances, it can make some slight changes in your output. But you can see the difference is showing up as mu1 minus mu2. The sample mean, that was our numerator, the 200. The standard error was that big square root in the denominator. So that was the 1264.911 whatever. Okay, degrees of freedom was 25. The test statistic, okay, and I cut this off from the StatCrunch output, but it's 1.58. And then the p-value was 0.1267. So before we just bound it between 0.10 and 0.20. Now we're actually getting the actual value, 0.1267. So what would you have to do if you were given this output as far as writing up the results? Well, you still begin with all the same stuff, right? You write down your null and alternative hypotheses. Okay, so H sub 0 is that the mean for north minus the mean for south is 0. The alternative is the mean for north minus the mean for south is not equal to 0. And then you can define what mu sub n minus mu sub s represents, and that would be the mean cost of all houses north of Center Street minus the mean cost of all houses south of Center Street in Provo. Your decision rule is to reject the null hypothesis if the p-value is less than or equal to your level of significance, 0.05. Your test statistic is still the t equals formula, but now you don't have to plug the numbers in and do the calculation. That's already been done for you, so you can just write equals 1.58. The reason I want you to get used to writing the formula down is because that's going to be a time to pause and make sure you look on the formula sheet and are thinking about working this exercise as an independent samples t-hypothesis test. And if you're thinking it should be dependent samples, this is a chance to slow down, look at the formula, recognize you're not doing the right thing if you're thinking this should be paired samples. Okay, so this is a chance to slow down and think about what you're doing. The p-value, again, we don't have to go to table T, it's given in the StatCrunch output, so it's 0.1267. Okay, this is valid because the sample sizes are random and independent. Sigma sub n and sigma sub s are unknown, and the populations are normal. Our decision and conclusion are going to be the same as before. Fail to reject the null hypothesis for the decision, and then at a 0.05 level of significance, there is sufficient evidence to say the mean selling price for all houses north of Center Street and Provo differs from the mean selling price of all houses south of Center Street and Provo. So at a 0.05 level of significance, you didn't have enough evidence to say that there was any difference between the mean selling prices for the houses in the two locations. Let's look at another example. So in this case, we're going to use the output from StatCrunch to determine if the mean time spent on patient care weekly is different between general practitioners and pediatric physicians. We're going to use an alpha level of 0.05. We can assume that a random sample of 79 general practitioners and 91 pediatric physicians were in this study or this survey. So you can see the output below. What we need to pay attention to is that general practitioners are first, pediatric physicians are second. The t-statistic is 2.685. The p-value is 0.008. And then we could actually get that t-stat by taking the sample mean, 1.380, divided by the standard error, 0.513932. Okay. Other than that, we can sort of peek ahead, see the p-value is small, so there is a difference. What we also would want to do is say, okay, well, which one is larger, right? Which one spends more time on average on patient care? Since the sample mean is positive, the t-stat is positive. The only thing that makes a difference in whether the t-stat is positive or negative is the order you do the difference in the numerator. The denominator, that standard error, is always positive. So the sign, positive or negative, goes with what was general minus pediatric in this case, but first number minus second number in that numerator. So if there's a significant difference, then you want to say which one was larger or smaller. In this case, general, we're going to be able to say general practitioners ended up having a larger mean. Okay, so what would the steps look like? Well, under the null, we would say mu sub g minus mu sub p equals 0. Under the alternative, we would say mu sub g minus mu sub p is not equal to 0. We would reject the null hypothesis if the p-value is less than or equal to 0.05. Now the test statistic, you would write down your formula, and then that equals just the number that you read out of the StatCrunch output, the 2.685. The p-value also, you just read out of the StatCrunch output, 0.008. Now this is valid because we had two random samples. We collected them independently. The population standard deviations are unknown, and we have large sample sizes. 79 and 91 are both more than 30. So because the p-value is less than 0.005, we're going to reject the null hypothesis. So at a 0.05 level of significance, not only do we want to say there's a difference, but since the t-score is positive, we're going to say the first mean, mu sub g, is larger than the second mean, mu sub p. But we have to put all this in just plain words. So at a 0.05 level of significance, there is sufficient evidence to conclude that the mean time spent on patient care weekly is more among all general practitioners than among all pediatric physicians. So that's another example of a t-hypothesis test to compare two groups with quantitative data.